To summarize the pH stainlesses, the advantageous part of these alloys is they tend to have better corrosion resistance. They're also magnetically hard. They have a moderate work hardening rate, but the more challenging aspect of cold working these alloys is the fact that they start at a relatively high strength. And they have moderate to high strength capability, and also some size change and distortion attributes with heat treatment. Again, just to give you a sampling of some of the main grades you would run into in this family of alloys, 17-4 is probably the one that most people are familiar with. It's an alloy that used to be, well, 10-15 years ago, it was a pretty novel, not so much widely used material to be almost a staple today. It's pretty much a commodity type alloy, but still very widely used in many fields. You can see that the constitution of these materials is quite a bit more complex than your standard Martensitic grades, and they operate a little differently from heat treat and strengthening perspective. But these are sample chemistries that represent typical ranges for the materials. 17-4, as its name implies, is roughly a 17 chrome 4 nickel material. It's strengthened with an intermetallic phase that's made up of a copper nickel compound. 13-8MO is a basically a version of material that requires remelting to gain some of the fatigue characteristics that the alloy is capable of. So when you get into alloys like 13-8 and 455 and 465, they're generally consumable remelted to get the cleanliness of the material, the micro cleanliness, to a point where the fatigue characteristics can be maximized. Custom 450 is somewhat similar to 17-4, a little different in composition, different in terms of the fact that it does have a little bit of moly and a little lower hardener content. The properties are generally the same. The advantages of 450 is the corrosion resistance is slightly higher, and the material does have the capability of being utilized in its solution annealed condition. It doesn't have to be aged to avoid stress corrosion cracking concerns. 455, also commonplace in medical, is a high strength lower corrosion adaptation, and it uses titanium as well as copper. And then custom 465 is one of the newer offerings in the marketplace. Offers the highest combination of strength and corrosion resistance available in a pH stainless steel. This is just a rough strength comparison of the materials, just to give you an idea in their peak usable strength conditions, what the differences are in yield and tensile capability, as well as damage tolerances represented in sharp EV notch values. So you can see that custom 465 is capable of, in the H950 condition, of values of up to 240 yield relative to 17-4 at much lower values in H900. So it gives you kind of a spectrum of what the strength capabilities of the materials are. So I've just given you a quick snapshot of some of the different materials available. This is just a very small sampling, but these are some of the most common players you'll run into. When you select alloys for your application, if you're talking about stainlesses, obviously you're concerned about how much corrosion resistance do I have and how much strength does the material give. And beyond that, you have to be able to make your parts. So we consider how can they be fabricated, what kind of machinability do I have, can I form, can I weld and braze. And there's any number of concerns that you'll have that will impact your choice. But one of the easiest ways is to plot corrosion resistance relative to strength. And what I did here is I took the different alloys and took some salt spray data. Salt spray it's a tough test to give as an absolute, but it is a test that can give you an idea of roughly where alloys are going to fall in terms of general corrosion resistance relative to one another. Salt spray, quite frankly, for most Martensitics, like the 440C, and I apologize if some of these numbers are hard to see, 420 and 410 are really a matter of hours typically. So it's really even too aggressive of a test to test those alloys. But they typically are going to fail in a matter of hours. When you start talking about a type 431 or a trimrite material, you're closer to a 100-hour alloy. And when you get into the pH stainlesses, which again offer a pretty good breadth of strength capability in terms of hardness, but also offer very good corrosion resistance. So that's the value of the pH stainlesses and why they're so widely used, is because they do offer the best combination of strength and corrosion resistance. For comparison purposes, Type 304 is commonly considered about a 200 to 300 hour salt spray alloy. Type 316 is an 800 to 1,000 hour alloy. So again, that's generally speaking, all things considered. Salt spray can be somewhat of a subjective test. You'll never have a materials manufacturer guarantee a salt spray number, and you'll have very few of them even give you data close to this that kind of gives you rough numbers. But this is a good comparison, all other things being the same. I threw some applications up here. I saw that the crowd was going to be largely composed of folks from medical companies. Martensitic and pH alloys are typically not candidate for implants. They just don't have that level of corrosion resistance, and you're probably well aware of that. The majority of these alloys are included in F899, which are surgical instruments, and really that spec is probably the most applicable industry spec from a medical perspective for these alloys. Some specific applications would include pumps, whether they be medicine pumps or blood pumps, needles, fixation, rasps for cutting away bone appliances, cutter tools, and dental tools. Other applications outside of the medical industry are very broad, and again, I just threw some up here. Fasteners are commonly cold-headed out of these materials. Sensors, firearms, cutlery, 440C and 420 are two of the main alloys you'll find in cutlery. I'm going to talk a little bit about heat treatment. Some of this is pretty rudimentary, but it does give some good rule of thumbs. Martensitic stainless steels are heat treated through quench and tempering, and in order to, that's kind of the lingo of the industry. Really what you're doing is austenitizing. You're taking an alloy that in its annealed state is primarily ferrite and carbide. You're heating it up so that it changes to austenite, which is face center cubic. The reason for that is if you look at an iron-carbon phase diagram, the solubility of carbon in ferrite is very small, about 0.02%. Austenite has much higher solubility of carbon, plus you're at a higher temperature so the carbon can move around more readily. So you take the carbides and the carbon in the solution and you quench it from there, cooling it and freezing it basically into place in a metastable phase called martensite, hence the name Martensitic stainless steels. Usually this is done from 1700 to 1950. Rules of thumb, higher austenitizing temperatures generally maximize corrosion resistance. So quenching from 1900 to 1950 is commonplace. Lower austenitizing temperatures, though, are better used in conjunction if you're going to temper these alloys higher, because you will get better toughness and ductility of the material. Some heat treaters will, and I don't speak for any heat treaters in particular, but I've run into instances where customers have asked for an alloy to be used out of its normal hardness range. For instance, trimite used in the low 40s Rockwell. It's just not designed to be used there. So what they'll do is they'll austenitize slightly lower to get the hardness down and temper high, and that does compromise corrosion resistance, and in some cases stress corrosion cracking resistance as well.